Welcome. In this video, we're going to take a closer look at some of the properties and reactions of acids and bases. So the definitions are still debated, and you actually can get into some really funky definitions if you look at Lewis acids and bases, which we won't. But the properties and reactions are well understood for both, regardless of how you define an acid and base. Now, alkalis are slightly different than a base, at least technically speaking. A soluble base that releases OH ions when dissolved in water is an alkali. So technically speaking, only an arrhenius base can be an alkali. So bases are technically defined as H plus acceptors or electron pair donors. So most bases are soluble and are alkalis, but not all bases are alkalis, like NH3. Even though it may be soluble in water, it is not going to release an OH minus ion, but it will accept an H plus ion. So bases we'll study are those that neutralize acids to produce water. Excuse me. So metal oxides, I don't know why I have this alkali here. That makes no sense. So let me just cross it off. So bases we'll be studying are metal oxides, and metal oxides are just what they sound like. It's a metal combined with oxygen. So like sodium oxide, potassium oxide, magnesium oxide. So Na2O, MgO, CaO, whatever. Metal hydroxides, which is just the metal combined with the hydroxide. Ammonia is kind of its own unique case because it picks up the hydrogen to become NH4+. And then soluble carbonates, which include just sodium and potassium carbonate, and the soluble hydrogen carbonates, which are going to be NaHCO3 and KHCO3. So those soluble carbonates and hydrogen carbonates are going to be limited to just the sodium and potassium, as very few of those are actually soluble. So reactivity of acids and bases. Acids react readily with three big groups: metals, bases, and carbonates. And with all three, they form salts. And salt is kind of a generic term used to form a compound, to describe a compound formed when the H plus ion from an acid is replaced by a metal or another positive ion like NH4. So it's really just an ionic compound. Parent acid is used to describe the relationship between the original acid and the new salt. And you can also say parent base when it's neutralization. For example, if you mix HCl and NaOH, you get water, and then the salt you get is NaCl. So we would say that NaCl formed from the parent acid HCl, or we could say it formed from the parent base NaOH, or you could mention both of them. So again, the three big categories of reactions by acids are acids plus metals, acids plus bases, and acids plus carbonates. And in each case, you get salt. And in the case of an acid and metal, you get hydrogen. An acid with a base gives you water. And an acid with a carbonate gives you water and carbon dioxide. And you're going to be expected to be able to generate all three of these reaction types. And they really aren't that difficult because they're basically just replacement reactions that we'll take a look at a little closer here. And I actually rearranged the order. This is the order the book gives them in. I rearrange it a little bit to get a mnemonic for each one. So I'm going to take a look at the first one on this video and then continue on part B of this video looking at the other two reaction types. So I rearrange it to metal plus acid gives you salt plus hydrogen, or MASH. And this actually is a very simple equation because when you remember that hydrogen has one valence electron, or a +1 oxidation number, and most metals have one or two electrons to lose, then hydrogen and metals can swap places. In fact, hydrogen is often placed on the metal activity series. So the reactivity of metals with acids varies depending upon the metal. So HCl with magnesium, really a vigorous reaction because magnesium is far more reactive than hydrogen. HCl with copper, not very vigorous because copper and hydrogen have similar reactivities. In fact, hydrogen is less reactive than many metals, so that means many metals will react in acid. HCl plus zinc, the zinc is going to bump the hydrogen off, being more reactive than the hydrogen. Iron in sulfuric acid, iron's more reactive than hydrogen, going to bump it off. So these really are just single replacement reactions. The metal and the hydrogen swap places and leaves you with the salt and hydrogen. And again, you just see the single replacement here between hydrogen and zinc, and then between hydrogen and iron. Last thing to mention on this video is this idea of complete and net ionic equations. The complete ionic equation is when you show what these aqueous compounds actually look like. Aqueous compounds have been broken down. The reason salt dissolves or disappears in water is because it becomes aqueous or dissolved. That means the water has literally pulled the ionic compound into its anion and cation parts. So the H plus and the Cl minus, those two ions are free from each other and floating around separately in that aqueous solution. So really, this equation 2HCl plus Zn gives you ZnCl2 plus H2. Really what you've got going on there is you've got 2 hydrogen ions and 2 chlorine ions from the HCl. You've got zinc atoms in their solid form. And when you get done, you have zinc ions, well, 1 zinc ion in the ratios here, with 2 chlorine ions, and then the hydrogen gas. So notice the coefficient 2 applies to both H plus and Cl minus on the reactant side, but on the product side, the subscript 2 is only the coefficient for Cl minus, because the 2 Cl minuses are going to be separated by water, but the hydrogen, being a gas, is still just H2. So 2HCl, the 2 distributes through to both ions. ZnCl2, the 2 only goes with the Cl minus. There's just 1 zinc with 2 Cl minus. And the H2 remains intact as a molecule because this is gas and it has not been separated into ions. So each ion must indicate its charge since it's no longer part of a neutral ionic compound, but your charges should cancel out. I've got 2H plus, 2 Cl minus, so I'm at a net 0 here. A 2 plus with the 2 Cl minuses, I'm back to a net of 0. And that brings us to the last idea of this net ionic equation. If we take a look at our equation up here, the Cl minus remains unaffected. It really is as if the Cl doesn't even know a reaction's going on around it. And unless you drove the water off of this, got rid of the water in this solution, there'd be no reason for the zinc and chlorine to reconnect. So right now, chlorine is oblivious to any change having gone on. Not like chlorine's alive or anything, but there's been no chemical change to chlorine in this reaction. So we call it a spectator ion, and we can actually cross that off. Zinc, on the other hand, has lost 2 electrons to become zinc ion, and each hydrogen has gained an electron to form hydrogen gas or hydrogen molecules. So here's an example for you to try. H2SO4 aqueous, iron solid, forms FeSO4 aqueous and hydrogen gas. So go ahead and pause and see if you can fill this out yourself, and I'll go ahead and write my solution in. So for the complete ionic, I'm going to have 2 hydrogen ions and a sulfate ion with a 2 minus charge. Fe solid is going to be unaffected. That's not an ion yet. On the other side, though, I'm going to have Fe 2 plus, SO4 2 minus, and then my hydrogen gas remaining intact. So my net ionic, I see that it's the SO4 that's the spectator here. So really my net ionic equation is 2H plus Fe yields Fe2 plus and H2. And in chapter 9, we're going to start looking more closely at these net ionic equations and where the electrons are going. So Fe is going to give up 2 electrons to the hydrogen to make hydrogen gas and iron ions.